Hello everyone and welcome back to this next lecture in the machines lecture series. And this is where we had left off last week, where we had created a few control files for the single phase induction motor simulation, and the load model was the model of the controllable current source which we had simulated before, and the induction motor model is currently a blank file which we had just created and gotten started off with. So if we go to the editor, we'll find that this is what we had done. So in this new folder which we had created for the single phase induction motor, the induction motor model will be the control file that contains the mathematical model of the induction motor, and load model.py will receive the current that needs to be generated. And this is how we're going to connect it. So in this lecture, we're going to slowly start building up the induction motor model from our equivalent circuit, which is this one, right? So let me now go back to the file browser. So as always, before I start the lecture, a little bit of brief background that if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length online courses which you can find on several MOOC websites. So to find the list of courses which I currently have, let me go over to my website, which is pythonpowerelectronics.com. And in this, we just have to click on the button called Learn. And this is the list of all the courses which I have currently. So the very first course I have is called Simulating Power Electronic Circuits Using Python. And in this, I talk about how you can use Python and Python Power Electronics to simulate simple power electronic circuits. The next course I have is called Basics of Digital Signal Processing for Power Engineers. And in this, I talk about how you can use Python and Python packages such as the SciPy package and the signal package within SciPy in order to be able to design filters such as low pass filter and notch filter for power engineering applications. The third course I have is called Simulation of Magnetics for Power Electronics Using Python, and in this I talk about how we can model and simulate magnetic components such as inductors, coupled inductors and transformers using Python Power Electronics. The fourth course I have is called Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and packages such as the Python control package to analyze and design controllers for power electronic applications. And the last course I have is called Why Specialize in Power Electronics, and in this I talk about the different challenges and opportunities in power electronics, and this is mainly a free and motivational course which is targeted towards either junior undergraduate students or even high school students who want to choose which domain they want to specialize in. So all these courses are available on two MOOC websites, which is Decibel Labs and Udemy, and you just have to click on the button here to go to the course link. So the link for this page is provided in the description for this video. If you're interested, please check it out. So with this, let me go back to the simulation. So as I already said, we have this load model.py and we only have to make one small change to it, and that is to add a variable storage element. So this will come later. For now, let's go back to the induction motor model and start building it. So if we look at our equivalent circuit, that is this one. This is the equivalent circuit that we are going to use to simulate the induction motor, right? And as I already said, that everything to the right of this circuit is the induction motor model and to the left is merely the single phase supply. So the first thing we need to do is we need to actually calculate these equivalent circuit parameters. And as I already said, there are ways to do this using no-load test and block rotor test. So if you have a physical motor and you have a laboratory, you can perform these two tests and calculate the parameters of the equivalent circuit. In our case, however, we are going to use the process of estimation. So let me first go back and start writing some basic parameters of the induction motor model. So now different induction motors will be specified in different ways, but there are some main ratings that you can find in almost every induction motor, right? So first I'm going to write down motor ratings, and these motor ratings are usually manufacturer specifications. So either you can find them on the manufacturer specification plate, which is actually a metallic plate on the induction motor, or you will find them on separate documents provided by the manufacturer, whichever, right? So the most important is, of course, let me remove this, is V rated. This is the rated voltage of the induction motor, right? Now, depending on where you live, this will be either 120 volts if you're in the US or Canada, or it will be 240 volts if you're in Europe, or it may be 230 volts in India, and there are other parts of the world which use slightly different voltage ratings. So since I am in Germany, I'm going to use 240 volts. Now it's important to note always, this is the RMS single phase voltage rating, right? So this is typically the voltage that you will get if you were to connect it to your domestic power outlet, right? So if you want to know what is your rating, just check out where you are geographically and you'll be able to find out what is the single phase voltage that you actually get in your domestic power outlet. So now that you have this, the next thing which we need to do is the rated power. Now the rated power, however, when you say the rated power, it is usually the output rated power. This is also usually available on the specification, the manufacturer specification plate, which is on the induction motor, or as I said, on separate documents that you can download. Now, since this is a single phase induction motor, your ratings can vary depending on the application. You can have motors which are just a few hundred watts, right? Or you can have motors which are few kilowatts depending on the application. For example, a simple single fan could be just rated for a few hundred watts because you don't need that much. Whereas a pump that actually pumps any kind of liquid like a fluid or maybe water or anything else might need something a little higher, right? So let us choose around 2500 watts. And just give this a little spacing here. And this is in watts, right? This is the output power. Now that we have the output power, for most of our application, this is the mechanical output power. So this is the mechanical output power that the machine can generate. Now, we need to find out the input power, right? Now the input power can be found out in various ways, and that is mostly through the efficiency. So we need to know the efficiency of the induction motor at the maximum power rating. Okay. Now this usually can be found in a manufacturer documentation where they perform several tests on the induction motor and they provide several efficiency curves, right? So usually you will find an efficiency curve which is the efficiency versus the output power. And usually any motor is designed to produce maximum, or rather designed such that it will be most efficient near the maximum rated power, right? So efficiency I can write as N. It's actually neta, right? But I will just write it as N. Actually, maybe I should write it as EFF. Efficiency rated. And here I'm going to make an assumption. If you have a physical motor, I would suggest check out the documentation, or you will have to perform an experiment. That is, you will have to load your motor throughout from 0 to rated and calculate the efficiency at each and everything. And also you can find out the input power. However, I don't want to do that, so I'm going to use an estimation method. Again, induction motors can be rated anywhere between, efficiency usually varies between around 75 to 90%, right? Like I said, the maximum efficiency or the best efficiency is usually close to the rated efficiency because most manufacturers will expect you to run your motor close to the rated output power. So a fairly reasonable guess is 85%. So this means 85% efficiency at max output power. So now that we have the efficiency at rated output power, we can of course calculate the input power by this simple calculation. Right? This is the input power. So we now have the rated output, rated voltage, the rated output, and this is usually always provided. And the efficiency rated can be calculated either through an experiment or you can check out if your manufacturer has provided you any data sheets. Now, after this, a very important specification is the speed, N rated. And I realized that I needed to use N for speed, which is why I didn't use it for efficiency. Now, the N rated again depends upon the number of poles that the induction motor has. Alright. Now, an induction motor can have any number of poles, which means the simplest is 2. Always poles are in multiples of 2 because you can't have an odd number of poles. Always magnetic poles come in pairs. So you can have 2 poles, you can have 4 poles, 6 or even more. Now the basic is a 2-pole machine. Now before I write N rated, let me write the number of poles. Let's see, number of poles, and this can be, let's say, 2. Because let's start with a very simple one, which is just 2-pole machine. We can then later take another more complicated machine, which is a 4-pole machine. Now, once you have the number of poles, we can find out the synchronous speed, right? So let me write that down, synchronous speed. The synchronous speed of the motor can be found with respect to the frequency and the number of poles. So now that I have specified number of poles, I also realize I should also mention the frequency. So F rated is the rated frequency of the induction motor. Again, this depends on where you live. If you're in North America, US or Canada, it's probably 60 Hertz. If you're in other parts of the world, it is 50 Hertz, right? So just going to put a comment saying Hertz. So now that we have the frequency and the number of poles, we can calculate the synchronous speed. The synchronous speed is usually calculated as 120 into F rated divided by number of poles, right? Now this will give us the synchronous speed in revolutions per minute. This is usually how it is. Now this 60 comes because we are calculating in minutes. If you want revolutions per second, it will be just 2 FP, right? Because the 60 then gets rid of. Now if you want to know more about this, I would suggest all you have to do in terms of synchronous speed is just do any basic Google search, and this will tell you how the synchronous speed of any system comes with respect to the number of poles, right? Now this is something that I will take for granted, but I would say that this is a fairly basic computation. If you need to know more, just Google or read any textbook. Now that we have the synchronous speed, we can find out another thing which we need to do is we need to calculate how much will be the synchronous speed. So for a 2-pole machine, 120 into frequency 50 divided by 2 is quite simply equal to 3000 RPM, revolutions per minute. It's also called RPM. Now in an induction motor, the speed will usually be less than the synchronous speed. This is when it is in motoring operation. When a induction machine behaves as a generator, in that case the speed will be greater than the synchronous speed, and that's when the slip is negative and power is being fed to the grid rather being taken from the supply, right? So in our case, since we are considering a motor, we can specify the rated speed less than the synchronous speed. Now a safe bet for a 2-pole machine which has a synchronous speed of 3000 RPM is 2800 RPM, right? And let me put a little comment here. It is in revolutions per minute. And let me leave some space. So these are the most basic ratings of the induction motor, right? Again, if you have a physical motor, check it out and you will find these ratings, that is a voltage rating, the output rating, the rated speed, the number of poles and the frequency to be provided right away. The efficiency at rated power will something that you either have to understand through an actual experiment or through a data sheet, right? But these are the ratings that we are the most basic, and in almost every induction motor you can find this either by just reading the nameplate or by downloading datasheets. Now, since this lecture has already gotten a bit long, I will stop with this. But for now, what I would like you to do is, if you have any motor which is physically available with you, if you are a student and you are in a laboratory, you have a laboratory, check out what are the ratings of the induction motor which are available and compare with these ratings which I have written down to find out which ratings can be directly read off the machine nameplate and which of those you would need to measure or either find out through any other data sheets. If you do not have a machine available with you, go through some manufacturer websites and look for single phase induction motors which are available for sale. Right? Many of the big companies like Siemens and ABB and GE sell induction motors, and so you can go on any of their website and check out what are the motors that are available for sale and what are the ratings of these induction motors. This will give you an idea of how we can actually define the ratings in an induction motor simulation model, so that this simulation matches with a physical motor that you would actually either purchase or you would find in your laboratory. So with this, I will end this lecture. In the next lecture, we will continue using these ratings and starting to calculate the equivalent parameter, or rather the parameters of the equivalent circuit. Like I said, I would like to take it very slow and easy, because always any machine can get a little complicated, right? And it's very important that we spend time with all these physical parameters to totally understand what are these parameters and how they are translated to a mathematical model that we can simulate in and actually see simulation results. So if you have any doubt, either send me an email or message me on social media, whichever is your preference. Otherwise, I will see you next week, where we will continue to calculate the parameters of the equivalent circuit. Thank you so much for watching, and see you soon. Goodbye for now.